Section 3-8 is on the derivative of sine and cosine. The objective of this section is to derive the trig rules for the derivative of sine and cosine. If you recall in section 3.7, we talked about those. It actually was introduced in 3.6, but we proved, I guess, graphically what the derivatives of sine and cosine are, and we're going to take an algebraic approach now to prove those. And then it says also to find the derivative of sinusoidal functions in real-world problems. So we'll look at some real-world phenomena that can be represented with a sinusoid. A sinusoid is just simply a transformation of sine or cosine, and then use a little bit of calculus on that function to evaluate different things, different rates. All right, so let's take a look at a special limit property that we need to work with first. We'll show you the property here and just talk about it, and we'll also look graphically and numerically on the calculator why this limit property is the way it is. But we'll look further at this in the second half of this section here. So here's the property that you need to know. Turns out that the limit as x goes to 0 of sine of x divided by x is equal to 1. Now again, we're going to take a look at this both numerically as well as graphically to help illustrate why that's the case. But we'll deal more with the formal algebraic proof of this in the second half. So let's flip over to our calculator. And in y1, let's put in the function sine of x over x. And I'm going to set my window up here. We'll go from -10 to 10 for our x's, and we'll go from -4 to 4 should be fine for our y's. We're saying the limit's 1, so this should give us a decent sketch of that graph. And if we graph this thing, here's that graph, and you can see that as we approach the x value of 0, that is, as we're getting closer and closer to that y-axis, you can see that the function from the left side and the right side appears to cross the y-axis there, or approach a value of 1. Okay, so graphically it looks like the limit is 1, as we stated it is. You can also do this numerically by using your table. And let me just start out my table at 0. And I'll make a really, really small change in my table, like 0.01. And I'm just going to go to the table and just have it generate a list of values here. I'll kind of scroll back here a little bit so you can see the values that we're approaching from both the left and the right side of 0. But I can see that we're at 0.99985, and then it's 93 as the last digits, and then 98, and so forth. So it looks like we're getting closer and closer to 1 from the left side. And you can see it's the exact same values from the right side. It looks like we're approaching a value of 1. Of course, we're undefined at 0 because of the fact that you'd be dividing by 0 there when x is 0. But it appears as though the limit is 1 then. Okay, so there's a graphical and a numerical approach to explaining why the limit of this is 1, but we'll look at the algebraic proof of it in the second half. All right. That brings us to then the derivative of sine. Now again, we looked both at both sine and cosine back in section 3.6 and analyzed their derivatives numerically using that nderiv command on our calculator. And it appeared that when we started out with f of x equals sine of x, that the derivative, f prime, turned out to be cosine. The graph looked like cosine. We graphed the cosine function along with it. They appeared to be right on top. Cosine appeared to be right on top of that numerical derivative, so it looked like that was the derivative function. We're going to go through and actually prove algebraically here that that, in fact, is the derivative. All right, so as we've seen with a lot of these theorems or properties that we're working with, that one thing that we are doing when we do a direct proof is we start out by stating the condition or the hypothesis of that theorem. So we're going to say let f of x equal the sine of x. All right, and the conclusion of this is to prove what f prime is equal to. So let's just start out with the definition of what f prime of x is equal to. It's the limit as h goes to 0 of f of x plus h minus f of x all over h. And as we've seen many times now, the first step of this is to replace function f with what it's equal to. So I have the limit as h goes to 0 Now f of x plus h, that says take your function f and replace each of the x's in there with x plus h. So this is going to be the sine of x plus h minus the sine of x. And that's all divided by h. Now, algebraically, there's nothing more I can do with this in the form that it's in. Sine of x plus h minus sine of x, there's nothing I can do to simplify that any further. I need a property, or a trig identity is really what I need, that tells me how I can rewrite this. And we had several properties, several trig identities that you learned back in pre-calculus. And in this case, we have one that tells us how to take the difference of two signs. I have the sine of one quantity minus the sine of another quantity. Rewrite that difference as a product. Okay, and if you've forgotten these, they are actually in the back of your book. In fact, I'll make a note of that here for you, that your trig identities are in the back of your book. They're actually on page 659. If you want to flip back there to see those, you can. But the one that we're going to use is stated something like this. It's the sine of A minus the sine of B. Again, it's the difference of two signs. Sine of one quantity, so for us the A is representing x plus h and the B is representing the x. Turns out that that's equal to 2 cosine of 1/2 of A plus B times the sine of 1/2 A minus B. So that's the property that we need, that we're gonna use here. Okay, so going back to, I'm just gonna draw an arrow here to indicate we're gonna continue on from where we left off there. This is just kind of a little side note here for us, that we're gonna use that little property here. All right, so this is equal to the limit as h goes to 0. Again, sine of x plus h minus sine of x, I'm gonna replace it with what we just wrote down here. It's 2 cosine of 1/2 A plus B. Now A again is the x plus h, and the B is the x, times the sine of 1/2 A minus B. Again, A is the x plus h, and B is the x. And that's all divided by h. All right, so the next step of this is to do a little bit of simplification with that numerator there. So I'm going to write it as 2 times the cosine of, I'm going to simplify what I'm taking the cosine of. I can see that I've got 1/2 of this quantity, and that quantity has x plus h plus x. So there's actually 2 x's in there, but I'm taking half of that whole thing. So half of 2x would just give me an x. And then I have an h, but again, I'm taking half of that h, so I'm going to write that as h over 2. You can write it as 1/2 h if you want to write it that way, same thing. And then for sine, let's do the same thing here. Again, I've got an x plus h minus x. So the x's there cancel out, actually. So all I'm left with actually is 1/2 of h. I'll write that as h over 2. And we will divide that all by h. Now, what I want to do is factor out of that numerator. I want to factor out the cosine function. We'll see some nice things are going to happen here as I do that. What kind of leads me to that is the fact that I know I'm trying to prove the derivative of this is equal to cosine. So that's what's going to try to help me lead me to that fact that I want to pull out cosine to get it by itself, and then hopefully I can get rid of the rest of the stuff that's there. So I'm going to write this as the cosine of x plus h over 2 times, and then I have 2 sine of h over 2 divided by h is what's left there. Now what I want to do is, I could have done this in that same step, but I'm going to separate this just so you can see what's happening here. What I want to do is focus on this little 2 here that I've got, that I'm multiplying the sine by, and I want to rewrite that. So it's the limit as h goes to 0, the cosine function stays the same, and that 2 I'm going to change its location here, multiplying by 2, which is how I've got it written here, 2 times the sine of h over 2. Multiplying by sine is the same as dividing by its reciprocal, dividing by a half. So I can rewrite this as the sine of h over 2 divided by h over 2. Multiplying by 2 is the same as dividing by 2. So all we did is move that 2 to the denominator. But you can see now I have the sign of one quantity, h over 2, divided by that same quantity. All right. Now what I see I have here is the limit of a product of two things, the product of this cosine times that sine over h. So let's use our property for limits that says the limit of a product is equal to the product of the limits. So this is the limit as h goes to 0 of the cosine of x plus h over 2 times the limit as h goes to 0 of the sine of h over 2 all over h over 2. Limit of a product is equal to the product of the limits. And actually we're ready to evaluate these two limits just in the form they're in now. If I let h go to 0, just using substitution, I'll have a cosine of x plus 0 over 2, of course, which 0 over 2 is just 0. So there's where the cosine of x is going to show up. The second part of this, I'm letting h go to 0, and I have the sine of some quantity, h over 2, that's heading to 0. So that's basically heading to sine of 0. Divided by 0 over 2, that's heading to 0. So I have a limit that ends up in the form of sine of 0 over 0. And if you go back to that very first limit we talked about at the beginning of this section, that's the same limit. And so it turned out that limit was equal to 1. That's the reason why we had to talk about that limit to start off with. So to rewrite this then, this just becomes the cosine of x. And that's what we're trying to prove. Prove that the derivative of sine is equal to cosine. We've done it. All right. That's only half the work, though, of course, because I also need to prove that the derivative of cosine is equal to the opposite of sine. This says if f of x is equal to cosine of x, then f prime of x is equal to the opposite of sine of x. All right, and we're going to go through and prove this one. Now, to prove this, we could go through basically the same steps we just went through for proving what the derivative of sine was equal to. That's a little bit tedious, a little bit of extra work there that we don't necessarily have to do in this case, though. Because one method that we can use to prove something is if I've already proven one property, I can use that to help me prove another property. So we've already proven that the derivative of sine is cosine. We've done that. And I think I can use that to help me prove the derivative of cosine is the opposite of sine, to prove this property. So let's write down what we're starting with. F of x is equal to the cosine of x. And in order for me to use that property, I have to somehow rewrite cosine as a function of sine instead. Well, again, if you flip to the back of your book there and look through those trig properties, you'll find some properties called the cofunction properties. And the cofunction property for cosine of x turns out is equal to the sine of pi over 2 minus x. Okay, now this comes from what are called complementary angles for the two non-right angles of a right triangle. Turns out that this property is true. Okay, so I'm able to rewrite cosine in terms of sine. And if you look at what I have here now, I've actually got a composite function. The whole thing is a composite function. And I know how to find the derivative of composite functions. That's chain rule. The outside function is sine, which we just went through and proved what the derivative of sine is. The inside function is a linear function. And we know how to take the derivative of linear functions, so we are all set. I can take the derivative of the function written in this form. So let's use the rules that we already have in place to find that derivative. So follow chain rule. Chain rule says it's a three-step process here, remember. Take the derivative of the outside function. Derivative of sine is cosine. And I like using those parentheses as a placeholder here as I take this derivative. So first step, take the derivative of sine, which is cosine. The second step is to substitute in or evaluate, however you want to say that, at the inside function. So inside those parentheses, we put the pi over 2 minus x. That's the second step of chain rule. The third step then is to multiply by the derivative of the inside. So pi over 2, that's just a constant, so its derivative, of course, is 0, minus the derivative of x. Derivative of x is 1. So we end up with, when we rewrite this, I'm going to take that negative 1 and put it out front. We'll have a negative cosine of pi over 2 minus x, which isn't quite what we were trying to prove. We were trying to prove that it's equal to the opposite of the sine of x. But again, if you go back to those cofunction properties, similar to the cofunction property we started with, turns out that the cosine of pi over 2 minus x is equal to the sine of x. So this is equal to the opposite of the sine of x then. And that is what we're trying to prove. So with the use of that cofunction property, and then using the derivative of sine that we've already proven, we can actually prove what the derivative of cosine is equal to. And we'll do this many times there. We'll use a previously proven theorem to help us prove a new theorem or find a new property. All right. That leads us to what is called the general sinusoidal equation. And now that I know the derivative of sine and cosine, I can now come up with some real world phenomena that can be represented with a sinusoidal curve. That is a transformation of sine and cosine, and use it to answer some questions about that particular phenomena. All right, so let's take a look at our general sinusoid. Now you can write this in terms of sine or cosine. We're going to do this in terms of cosine, and I would suggest that you do that as well. But we have y is equal to c plus a times the cosine of b times x minus d. Okay, now the a, b, c, and d there all represent translations and dilations. That is, a translation is a shift of this function, or a dilation is a stretch of this function. And there's 4 of them because of the fact that some of those are vertical, some of those are horizontal. So you have vertical and horizontal dilations and translations taking place there. All right, so let's look at what each one of these represent here for us. So let's just go in order here, alphabetical order, I guess is what we're going to do. So the amplitude is actually the absolute value of A. Now the amplitude there is always positive, and that's why we take the absolute value of A, because A could be negative. So basically ignores the sign there of A to get the amplitude. And that value there, notice that you're multiplying A times the cosine function. That's a vertical stretch then, a vertical dilation is what I'll write here. It's a vertical dilation of that function. Okay, so the amplitude actually indicates the vertical dilation, but with a sinusoid we call it the amplitude. All right. If you take a look at what B represents, now actually the period is equal to 2 pi divided by the absolute value of B. And again, B could be positive or negative. So that's why we have to throw away the sign there, because the period is always positive. You could solve this for B. In fact, I'll just go ahead and write that next to it here. We could say, or the absolute value of B is equal to 2 pi divided by the period. You can write it either way. Okay. Now what the B actually represents, you notice you're multiplying the B times the x minus d there. And so since you're affecting the x value there, that's actually a dilation horizontally. And it's actually the reciprocal of the horizontal dilation. Okay, and because of the fact that we write it as just B, that's why it turns out to be the reciprocal. If we wrote that as 1 over B, then B would actually represent the horizontal dilation. But it's not written that way. That's just by tradition. That's how we write it, so we are not going to change it here. But it's actually the reciprocal of your horizontal dilation, how much you stretch this thing horizontally. All right, the next one is the value of C. And C is what we call the sinusoidal axis of this sinusoid. Another way to describe that is a vertical translation. You'll notice that you're adding that value of C to your cosine function, so it's actually the vertical shift up or down of this function. But we call it our sinusoidal axis. And the last piece there is what we call our phase displacement. And that's what D is. D represents the phase displacement. Or again, you can see that you're subtracting that from x, so it's actually affecting the x value. That's the horizontal translation. Okay. So in blue there, what I've written down, those are the, in terms of translations and dilations, what we're actually getting. But the terms that we use to describe this with a sinusoid is what we have written here: amplitude, period, sinusoidal axis, and phase displacement. All right, one last piece that we talk about with a sinusoid is the frequency. And the relationship between the frequency and the period is that they are reciprocals of each other. So the frequency is 1 over the period, or literally that would be the absolute value of b divided by 2 pi. If you just wanted to literally take the period that we wrote up above there and just reciprocate it, that's what you'd end up with. Okay, so if you're asked about frequency, usually what we do is find the period and then just reciprocate that, and you got yourself the frequency. Or vice versa. If they give you frequency, reciprocate that. That tells you the period. All right, let's draw a sketch of this to kind of fill in all the details here of what we're actually talking about and how each of these pieces fit into this particular graph here of a sinusoid. So let's sketch a sinusoid. I'm not going to worry about sketching something too accurate, but we'll sketch at least one period here of a sinusoid. And so let's start with the vertical part of this here, the vertical dilations and translations, if you will. So this line that goes right down the middle of this is called the sinusoidal axis. That's what that value of C is. C is the sinusoidal axis. Now here I've drawn it as C as a horizontal line. Doesn't have to be that way. C could be some function, like a linear function, so this actually would have a slope to it. Or it could be any other function for that matter, which means your sinusoid would oscillate back and forth around that sinusoidal axis, whatever that curve is. Most of the time we'll find it's going to be just a horizontal line or a straight line. Could have a slope to it. And then if you measure that distance from the sinusoidal axis to what we call here our upper bound, I guess we can continue this all the way over there. Or if I measure that same distance to the lower bound from the sinusoidal axis, that distance right there is the amplitude. So this distance right here is the absolute value of A. This distance right here is also the absolute value of A. So if you want to name these points here, this would be C plus the absolute value of A, and this would be C minus the absolute value of A. Okay, so that marks what's going on our vertical axis there, the amplitude and the sinusoidal axis. And then on the x-axis, on our horizontal axis, with the cosine function, what you need to find is where the maximum occurs. So I'm going to just pick one of these. It doesn't matter which one you pick here. I'm going to pick this one right here. And that maximum actually tells you the phase displacement. That's the d value. Okay. And then the last piece to this is to determine the period, which again, the period is the distance in this case from one maximum to the other next maximum, tells you the period. So this distance horizontal here is the period, which of course is equal to 2 pi divided by the absolute value of b. So I guess if you wanted to name this point here as d plus that 2 pi over the absolute value of b, you could. That usually isn't necessary to name it, but that would be the name of it. Okay, so there's the A, B, C, and D and how they all fit into our graph. So given the graph of a sinusoid, you should be able to come up with the values for A, B, C, and D, thus get your general sinusoidal equation, and then be able to do some calculus with that. So let's try that with an example here. Look at example 1 there on page 110. It says you have a mass that's bouncing up and down on a spring hanging from the ceiling. Its distance, y, in feet from the ceiling varies sinusoidally with time, t, in seconds, making a complete cycle every 1.6 seconds. And it says at t equals 0.4, y reaches its greatest value of 8 feet, and the smallest y gets is 2 feet. So they've given you a verbal description of this function. Remember we talked about different ways to represent functions? They've given us a verbal representation of that function. I want to take that and create a graphical representation of the function. So I can then take that graphical representation and come up with the algebraic representation or the equation of that function. Okay, so there's kind of a multi-step process that we're going to go through here. So let me first start out with a sketch of this thing. Now, for part A, it says to write an equation for y in terms of t. So that's the goal here. So that's why I'm going to start out with the sketch of this thing. I'm just going to mark, I'm not sure exactly what my axes look like here. It really doesn't matter. I'm just going to simply sketch a general sinusoid in here and just mark in the values that they've told us. So they said, starting with the first piece of information they gave us, it says it makes a complete cycle every 1.6 seconds. So in other words, the distance from this point to this point is 1.6 seconds. So this is 1.6 seconds. In other words, the period is equal to 1.6 seconds. The next thing, it says at t equals 0.4, y reaches its greatest value of 8 feet. So right here has got to be 0.4. At t equals 0.4, it says that you reach the greatest value of 8 feet. So that's 8 feet up here. And finally, it says the smallest y gets is 2 feet. So the lower bound for this function then is 2 feet. Okay, so with that, I've got basically all the pieces that I need to come up with the equation. Let's just add in a couple of other details here. First of all, the sinusoidal axis is the line that goes right down the middle of this. So that's the midpoint from 2 to 8 there. If I just find the midpoint value or average those two numbers, I can find the midpoint that I'm looking for. So 2 and 8 gives me 10. Half of that is 5. So 5 must be the sinusoidal axis. Not only that, but I'm going to need to know my amplitude. And so the amplitude, remember, is the distance from the sinusoidal axis to your upper bound or lower bound, whichever one you want to look at. So from 5 to 8, that's 3 units there. That's my amplitude for this function. The phase displacement I've already got marked. That's the 0.4. And the period I have is 1.6. And I can use that to come up with my value for b. All right, so that's the pieces that I need in order to come up with my equation. And they said that y is a function of t here is what we're working with. So I'm going to write it that way. I'm going to write it as y of t here, just to use a function notation when I write it. And the general equation, I guess I'll go ahead and write the general equation again, and then we'll just fill in the details. So it's c plus a times the cosine of b times t minus d. They said to use t here. So let's write our equation then. C, the sinusoidal axis we said was 5, plus a, the amplitude is 3, times the cosine of b, remember, is equal to, or really the absolute value of b is equal to 2 pi divided by my period. So it's 2 pi divided by 1.6 is the period that we have from up above. And that's times t minus the value of d, which d is your phase displacement, which is where that maximum occurs, is at 0.4. So there is our sinusoidal equation. And I would leave that, as far as the value of b is concerned, I'd leave that as 2 pi over 1.6. It's nice to write it in that form because if it's 2 pi divided by some number, that number you're dividing by is the period. So I'd leave it just in that form. Don't try to simplify it. All right, for part B now, it says to write an equation for the derivative, y prime. So now that we have y, we should be able to find the derivative of it. Y prime of t. So the function that we're looking at here is actually a sum of two functions. It's 5 plus 3 times that cosine. So we have, first of all, the derivative of a sum to deal with. So derivative of the first function, derivative of 5 is 0, plus derivative of the second function. Now the second function is 3 times cosine. That's actually a product, or excuse me, it's actually a constant times a function. It is technically a product of those two, but it's a constant times my function. So my rule is the constant stays out front times the derivative of my function. Now look carefully at the function you see there. That function is actually a composite function. You have cosine as the outside function, and all of this, which is actually a linear function, it's just 2 pi over 1.6, that's some constant, times t, and then minus that constant at the end there. So that's a linear function, mx plus b. So use chain rule to find that derivative. So derivative of my outside function, derivative of cosine is a negative sign times, or not times, but I'm going to evaluate that at the inside function. Derivative of the outside is the first step of chain rule. Evaluate at the inside, 2 pi over 1.6 times t minus 0.4 is the inside function. And then we multiply it by the derivative of the inside. which if you look at the inside function, it's really a constant, 2 pi over 1.6 times some function. So just follow your rule for the derivative of a constant times a function there. The rule is the constant stays out front times the derivative of our function, which derivative of t is 1 minus the derivative of 0.4 is 0. Or in other words, you'll notice that the derivative of that inside turns out to be, because it's a linear function, just that coefficient in front of t. It'd be the 2 pi over 1.6. Let's just rewrite that here slightly. I'm going to go ahead and combine the 3 with the 2 pi over 1.6 there, so as well as the negative. I've got a negative 6 pi over 1.6 times the sine of 2 pi over 1.6 times t minus 0.4. There is our derivative. All right, let's see what it says for the next step of this. It says for part C, how fast is the mass moving for these values of t? Now again, y tells you the location of that mass. It tells you the distance it is from the ceiling. So the derivative is actually telling you the rate at which the distance is changing. It's telling you the speed or the velocity at which this thing is moving. So all I got to do is take my derivative function and plug in these values here. So they wanted to find the derivative at 1. We'll use our calculator, by the way, to do this. So I'm just going to write down what we're going to calculate, and then we'll punch it in our calculator. And they wanted me to evaluate it at 1.5, and then finally the derivative at 2.7. So let's see what we end up with. Let's take our calculator and we'll plug into y1 that derivative function we came up with. So we end up with negative 6 pi over 1.6 times the sine of 2 pi over 1.6 times t minus, or x minus for our case here, x minus, forgot what that value was here, just a second, x minus the 0.4, 0.4. Okay, so there's our derivative function in y1. Let's go to our table. I'm just going to put this into ask mode so I can just type in the values that I want. So I've got 1, 1.5, and 2.7. And so here are the 3 values we end up with. So at 1, we end up with a negative 8.330. Negative 8.330. At 1.5, it turns out to be 10.884. 10.884. And finally at 2.7, it was a negative 4.508. Negative 4.508. Those are the values that we end up with. All right. Now we should also indicate units here for these values. So going back to what they used for units in measuring y they said was measured in feet from the ceiling, and our time, t, was measured in seconds. So all 3 of these are measured in feet per second. And again, if you go back to the other way that we can write the derivative, remember y prime of t is the same as saying it's the change in y, dy, over the change in t. And that really helps you see the units here, that y is measured in feet divided by, we're dividing that by, t is measured in seconds. So that really tells us the units there if I go back to that fractional form to represent my derivative. All right, look at D. D says that t equals 2.7 seconds is the mass moving up or down, and justify your answer. Well, for part D then, I can see that at y at 2.7 from my previous work there was a negative 4.508. So because the derivative there is negative, that tells me my function must be decreasing. Okay? Since y prime at 2.7 is less than 0, then y is decreasing. Now it still doesn't tell me which direction the mass is going. That's the question. They didn't ask whether y is increasing or decreasing. They said, is the mass moving up or down? So you have to look at how they've measured y here. So I'm going to just kind of roughly sketch this picture that they gave you in the book there. You got this spring hanging from the ceiling attached to this mass here. And they said that we're measuring y as this distance right here, the distance from the ceiling. So if y is decreasing, that means y is getting smaller and smaller and smaller. So that means this distance y is getting smaller and smaller and smaller, which means the mass must be moving up. Okay? So the mass is moving up. Okay, and that's what they were wondering. Which direction is the mass going? Is it moving up or is it moving down? And that's the justification to our answer. You always have to go back and check to see how they've measured y to help you figure that out. Just because it's negative did not mean that it's moving up. In this case, we were measuring y from the distance from the ceiling to our mass. Realize that if we had measured that in a different way, I know they didn't measure it this way, but if we had measured from the floor, if we had said y was measured that way, now all of a sudden when y is negative, that means the mass would have to be moving down. Always go back and check how they measured that initial quantity y there. All right, finally, for part E. E says, what is the fastest the mass moves, and where is the mass when it is moving this fast? All right, so the fastest that it moves. So in other words, they're talking about the velocity, the rate at which the mass is moving, but I want to know when it's moving its fastest, when it's at its greatest, when it's at a maximum. Okay? So if I have some function here, we're just going to take kind of a little side note here. If I have some function that has a maximum, let's call this function f of x. This function has a maximum right here at this point. And the way that I can use calculus to help me find that maximum is to recognize that the slope at that point, if I sketch the tangent line, is 0. So at that point, f prime of x, its derivative, is equal to 0. So given some function, in this case f of x, to find the maximum of that function, you find where its derivative is 0. So in our problem, they're asking when is your, what is the fastest the mass moves? They're asking when you have the greatest velocity. When's the velocity at its maximum? So in order to find that, I have to find out when the velocity hits a maximum. When the derivative of velocity, that means, is at 0. All right, so we need to find when v prime, oops, I shouldn't call it v prime though, because we didn't use that name in our problem. We called it y prime here. That v of t is equal to, or velocity is equal to y prime. So we need to find out when the derivative of the velocity, that's the second derivative in this case, is equal to 0. First derivative is velocity. I need to find out when the derivative of velocity is 0. And that's the work that you need to write down. You could actually go through and find out this value algebraically, but I'd suggest that you use your calculator to help you do that. And so let's graph this and find out when the second derivative is 0. So in y1, we already have y1 as the derivative. Let's just simply calculate the numerical derivative of y1. And we want to find out when it's at its greatest here. So let's see here. I don't need to have the original function actually. I don't need the velocity necessarily to sketch with it. I guess I'll go ahead and leave it in there, but we can get rid of it. And let's graph this from like 0 to, I don't know, let's go out to 20 here. I'm not sure exactly how far we need to go out, but we'll go out to 20 and see what that gives us. And let's use our table to give us a list of values that our function is going to go through from 0 to 20. I'll set my table up to start out at 0. We'll change it by 2. We'll put it in auto mode, just so I can see a list of values that this thing's going to go through. So it looks like our original function starts at 11.7 and then goes to basically 0 there and then to negative 11.7. It looks like our second derivative here is taking on some more extreme values. That's what I want to actually track there. So let's go to our window, and it looks like if I go from something like negative, let's go negative 60 to 60. Seems like that will be a decent window of this. We'll see how decent it is. So there's our original function. So that's actually showing a lot more periods there than I really need here. I'm going to change that here. I don't need to see that many. I'm going to just stop that. I don't need to go all the way up to 20. Let's go from 0 to, looks like 0 to 5 would be a decent window of this thing. There we go. That's looking a lot better here. So that's the velocity function. We want to find out when we hit our maximum velocity. So our maximum velocity is when the derivative is 0, and you can see that as that derivative function right now is sketching. Anytime I hit a 0, you can see that your velocity function, the original one, must be hitting either a maximum or a minimum. All right, so the one that I'm going to focus on is the one that occurs somewhere between 1 and 2 there, it looks like. My velocity was at a maximum, and so I'll just calculate the, the 0. Again, this right here is the maximum I'm going after, that guy right there. And I can find that by finding where this derivative function is equal to 0. So we'll let it crunch that for us and see what we get. So it looks like that right at 1.6, we get a value of 0. So t equals 1.6. Now, based on what we know about our sinusoids and where they hit their maximums, we could have determined that without even using the calculator, but that's how we would do this for any other type of problem. So the question was, what is the fastest the mass moves, and where is the mass when it's moving this fast? So all we found so far was where, at what time it occurs. I need to actually find out what the maximum actually is there. So on my graph there, I'll just trace the original function, the velocity function, to 1.6, and we get 11.781. So y prime at 1.6 turns out to be 11.781. And again, the units for this are in feet per second. And as far as where this occurs at, in terms of the location of the mass, when we hit the maximum velocity, the mass is moving on its way down, and when it hits the very bottom of however far it's going to go, it hits a velocity of 0. On the way back up, when it gets as high as it's going to get, the velocity again hits 0. So it's halfway in between the maximum and the minimum points is where we're going to get these maximum velocities at. So it's halfway between the upper and lower bounds. Of y of t. That's where those are going to occur. Okay? All right, that is the end of the first half of this section for us.